Let us now discuss the roles of humans in interpreting, evaluating, and debugging machine learning. We start with model interpretation, interpreting how the model works. Why do we want to do that? Well, in supervised learning, models are often evaluated in terms of objective performance metrics such as accuracy, precision, or recall. However, even if a model performs well in terms of these criteria, users may hesitate to trust the model if they do not understand the model's predictions. This is especially the case in critical domains like health or criminal justice. When using machine learning for medical diagnosis, for example, predictions cannot be acted upon blind faith, as the consequences might be catastrophic. Let me give a real example. In the medical data mining contests held by KDD-COP in 2008, the problem was to detect cancer from mammography data. Analyzing the data for this competition, researchers find that the patient ID feature has tremendous and unexpected predictive power. They hypothesized that in multiple clinical studies, data was ordered with prior knowledge of the patient's condition, which makes the patient ID a very predictive feature, although it shouldn't be, because we cannot decide whether a new patient has a cancer based on when he comes to the hospital, right? This issue would be incredibly challenging to identify just by observing the predictions and the raw data, but it's much easier if explanations are provided. For different stakeholders of the machine learning system, there are many different reasons why we need model interpretation. For machine learning developers, model interpretation can help them know when the model fails and identify the bugs and thereby fixing the bugs. For developers or data scientists, being able to explain how the model works can also help gain buy-in from the customers or management. For domain experts and end users, understanding how the model works is essential for them to decide whether or not to trust the model. In certain cases, for example, getting loans from the bank, it's important for customers to know what they need to do in order to change machine decisions when they are not satisfied. For auditors, knowing how the model works can help assess the risks to decide if a model is eligible to be deployed. Now let's first take a look at what an explanation means. Explaining a prediction means providing qualitative understanding of the relationship between the instance's components and the model's prediction. In the case of medical diagnosis, an explanation is, a small list of symptoms with relative weights, symptoms that either contribute to the prediction or are evidences against it. Humans usually have prior knowledge about the application domain, which they can use to either accept or reject a prediction if they understand the reasoning behind it. In our previous example, if a doctor finds that it was the patient ID that drives model decisions, then he or she will choose not to trust the model. For many tasks where no specific domain knowledge is required, we can simply involve crowds. So crowdsourcing can be used to determine the trustworthiness of a prediction or a model using explanations. Note that we need to distinguish between explaining a prediction and explaining a model, because sometimes we need to make decisions whether or not to deploy the model at all, or choose between two models which one to deploy. But often the case, we need to assess the trustworthiness of individual predictions in order to assess that of the entire model. A good way to provide a global understanding of a model is explaining some representative individual predictions of the model. Here is an example crowdsourcing task to see between two models which one is better based on explanations. Looking at the two example decisions here in machine classification of email asceticism. Both models make the same decision. The first model looks at words like God, mean, courage in its decision, and the second model looks at other words like posting, host, etc. So which one do you think is better? The first one, right? So to evaluate the trustworthiness of a model, humans can be involved with given explanations. Question here is, well, how should we generate the explanations? To see that, let's first have a critical look at what a good explanation should look like. First, it must take into account human intelligibility. For example, if hundreds or thousands of features significantly contribute to a prediction, it is not reasonable to expect any user to comprehend why the prediction was made, even if individual weights can be inspected. In addition, to have explanations easy to understand, we need to have the data representation being comprehensible also by humans. For example, for image classification, we cannot show individual pixels to humans. So the input variables in the explanations may need to be different from the features used by the model. Interpretability also depends on the target audience. Machine learning practitioners may be able to interpret small Bayesian networks, but laymen may be more comfortable with a small number of weighted features as an explanation. The second requirement for an explanation is that it should faithfully describe how the model actually makes the decision. It is often impossible for an explanation to be completely faithful unless it is a complete description of the model itself. For an explanation to be meaningful, it must at least be locally faithful, meaning that it must correspond to how the model behaves for individual instances. We note that local fidelity does not imply global fidelity, meaning that features that are globally important may not be important in the local context, and vice versa. A pioneering work was done by Hibero, who proposed the algorithm LIME to generate explanations for individual predictions. What they do is the following. For data representation, they use words for language tasks and pairs of pixels for vision tasks. And then, to reduce the number of features in the explanation, they use a sparse linear model to approximate the actual model decision. To train such an explanation model, they seek for a trade-off between explanation faithfulness and intelligibility. For faithfulness, they optimize the explanation model such that the prediction is similar to what the original model predicts. And for the explanation to be intelligible by humans, they constrain the number of features in the sparse linear model so that the number of features presented to humans is not too many. Here is an example of explanation generated for image classification prediction made by Google's Inception neural network. The top three classes predicted are, electric guitar, acoustic guitar, and Labrador. You can see the highlighted pixels of images that the model is looking at in making each of these three classifications. We can see from the explanation that the predictions are quite reasonable. The model even learned to look at the different parts of the guitar when discriminating electric guitar from acoustic one. Amazing, eh? The authors also did some experimental work with workers from Mechanical Turk and find that explanation is very useful for workers both to select models and to improve model performance. So what they did is that for language tasks, they present to the workers with explanations for predictions and ask workers to identify words that do not make sense to them. They then retrain the model by excluding the identified words. And with just 2 iterations, model performance were improved by more than 10%. So the takeaway here is that with explanations, humans can not only assess the trustworthiness of a model, but also actively debug the model and improve the model performance.